The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Ladies and gentlemen, welcome to this lecture on nonlinear finite element analysis. In the previous lectures, I introduced you to nonlinear finite element analysis, to the solution methods that we are using in nonlinear finite element analysis, using primarily physical concepts. We are now ready to discuss the mathematical basis of the procedures that we're using to obtain solutions. Of course, this material is very complex, and there is a lot we could discuss. But let us have a go at it. We have a body that undergoes large displacements, large rotations, and large strains. So therefore, we consider the body to undergo very large motions. We will use a Lagrangian description of the motion of the body. Here, on this view graph, I have prepared schematically the body that we are looking at. Here, the body is in its configuration at time 0. Notice that the surface area of the body is described as 0a. The volume is described as 0v. The 0 being a left superscript. I should point out at this point that you will be encountering now a lot of superscripts and subscripts, and that actually makes the discussion somewhat difficult. And for that reason, I like to take now on this view graph just a minute to explain to you why we have a particular superscript, a particular subscript in that particular location, and what it means to us. So a left superscript here, as shown on A and V, means at time indicated by that, at the time indicated by that superscript. So here we have 0A, 0V once again, area at time 0, volume at time 0. A particular point here, point P, has the coordinates 0x1, 0x2, 0x3. Now notice that these upper zeros here correspond to the time, as I just pointed out, whereas 1, 2, and 3, of course, correspond to the coordinate axes. This is a particular material particle. This material particle will move with the body from time 0 to time t, as shown on this view graph. Of course, at this particular time now, the surface area of the body has become TA. T now meaning surface area at time t. And the volume of the body is TV. Notice that the coordinates of this material particle now are Tx1, Tx2, Tx3. We will assume later on in our actual solution that the solution up to time t is known. In other words, that the area, the volume, in fact the stresses, the strains at time t are known, and that we will want to march ahead one time increment to time t plus delta t. Notice the volume of the body now is given by t plus delta t v. The surface area is given by t plus delta t a. The coordinates of the material particle have now become t plus delta t x1, t plus delta t x2, and t plus delta t x3. Well, there's one very important point, and that important point is that we are considering that the Cartesian coordinate axis in which the motion of the body is measured remains stationary. You should always keep that in mind. In other words, here we have the Cartesian axes x1, x2, x3, and those remain stationary, whereas the body moves through those axes, through the, system of axes, and we want to, of course, solve for that motion. With the particle motion described by the coordinates that I just mentioned, we can now define the following quantities down here. We can say that Txi, the coordinates at time t of a material particle, are equal to 0xi both of those quantities, of course, we know already now what they are, plus TUI. TUI are just the displacements from time 0 to time t. Similarly, for the situation from time 0 to time t plus delta t, notice that these are now the displacements from time 0 to time t plus delta t. And we can, of course, talk also about the incremental displacements. The incremental displacements from time t plus delta t, or rather from time t, I should say, to time t plus delta t. And those incremental displacements are given by ui. Of course, the lower right subscript always refers to the axes. In other words, I goes from 1 to 2 to 3 for the u's and for the x's. Well, I mentioned already that the Cartesian axes are stationary, and I have prepared this view graph to point it out once more very strongly. The unit distances along the xi axis are the same for 0xi, txi, and t plus delta txi. That is also a very important point. Let's look at this very simple example. Here we have an x2 axis, and we have the x1 axis along here. Notice the units along this axis are 1, 2, 3, and so on. A material particle has initially the coordinates 2, say, of course then this being the length of 0x1. This particle at time 0 moves to time t by tu1, the way we just said it earlier, and of course the sum of these two quantities is equal to tx1. Notice that tx1 is measured along the same axis with the same unit distances as 0x1. And therefore, for this reason, we now use just x1 here without the left superscript to denote the coordinate axis. By the way, in my book, the textbook for this video course, I have frequently put here a t or 0. I feel now it is better actually to drop that superscript, because this description, the way I just explained it to you, I think is even better. Well, let us talk now then about the principle of virtual work. And now we want to look at the principle of virtual work applied to time t plus delta t. The reason being, of course, that we want to solve for the static and kinematic variables at time t plus delta t. We assume that we know the solution from time 0 to time t. We discussed in the previous lectures already the principle, and I like to now just review it once more, because it's just of utmost importance to very well grasp, understand what the principle says and how we apply it then. Here we have now the Cauchy stresses. I defined the Cauchy stresses earlier as the force per unit area. The ij, of course, mean coordinate axes, I and j, in three-dimensional analysis going from 1 to 3. T plus delta t means the Cauchy stress at time t plus delta t. These are the real stresses that we want to solve for. Here we have virtual strains. These are infinitesimally small strains referred to the configuration at time t plus delta t. This t plus delta t means a reference to the configuration at time t plus delta t. And here we have, of course, a t plus delta t dv, because we are integrating over that volume, which of course is unknown in the incremental solution. This is the internal virtual work, which must be equal to the external virtual work. Here is again the script r, and this script r at time t plus delta t is defined down here in the view graph. We are integrating over the volume at time t plus delta t the body forces, and these are the real body forces, or forces per unit volume, at time t plus delta t, multiplied by the virtual displacements, delta ui. And the integration, of course, goes over the volume at time t plus delta t. We're adding to this part the surface forces, forces per unit area, at time t plus delta t, multiplied by the virtual displacements on the surface, this capital S stands for on the surface, and this product is integrated over the total surface of the body at time t plus delta t. We assume that we know this part. Once we have imposed a virtual displacement, and therefore we can calculate the right-hand side. Corresponding to that virtual displacement, we obtain virtual strains, and therefore we can calculate also the left-hand side. And once again, the principle of virtual work says that the left-hand side, the internal virtual work, must be equal to the right-hand side, the external virtual work, for any arbitrary virtual displacements that satisfy the displacement boundary conditions. Of course, remember, as I pointed out earlier, in an earlier lecture, that the virtual strains must correspond to the virtual displacements. And here we have the virtual strains once again. On the view graph, we saw this stress, and I called it the Cauchy stress. Here you have it spelled out once more. It's the force per unit area at time t plus delta t. We also talked about the virtual strains. And the virtual strains here, this was a quantity, are defined as shown on the right-hand side. Let me once again point strongly out that we are differentiating here with respect to the coordinates at time t plus delta t. Of course, the j and the I coordinate. And also please recognize that this strain is really the infinitesimal strain tensor that you are very well familiar with in infinitesimal analysis, in infinitesimal displacement analysis, I should say, except for one difference, that we're using here the unknown coordinates at time t plus delta t. And that is spelled out down here, that we're using a variation in the small strains referred to the configuration at time t plus delta t. So really, if you are familiar with the principle of virtual work as applied in infinitesimal displacement analysis, then you recognize that the principle of virtual work now applied to large deformation analysis, large displacement analysis, is quite the same, except that we are applying it to the current geometry, the current configuration of the body. In my textbook, actually, I have a little note, a footnote, that you might also look at in the beginning of chapter 6, where I discuss this principle of virtual work, that one way to look at it is that you see a body you see the body in front of yourself moving through the stationary coordinate frame. Once again, the Cartesian coordinate frame is stationary. You see it move, you see the body move through that coordinate frame, and there's somebody standing taking a picture. And that picture is taken at time t plus delta t. And now you have a picture, and you apply the principle of virtual work to that particular configuration which has been captured in that picture. That's perhaps one way to look at it, at least one way that I like to look at it. In order to solve or to work with the principle of virtual work, we need to rewrite the principle really, because we cannot integrate over an unknown volume, and we cannot directly work with increments in the Cauchy stresses. The volume t plus delta t, remember, is unknown. And the reason why we cannot directly work or simply work with increments in Cauchy stresses is because the Cauchy stress is always referred to the current geometry, current configuration. So if we talk about the Cauchy stress at time t, then it's the force per unit area at time t. And the Cauchy stress at time t plus delta t is the force per unit area at time t plus delta t. Now you can't add a quantity that is referred to time t to a quantity that is referred to time t plus delta t, because the areas, the reference areas, have changed. And we have to somehow take care of that in our formulation. And for that reason, we introduce these two new quantities. The T0s is the second Piola-Kirchhoff stress tensor, and the T0 epsilon is the Green-Lagrange strain tensor. We introduce these quantities. Of course, these are well-known quantities. If you were to look into continuum mechanics texts, they have been described in many, many books. and they are well known for some time, but we have extracted basically this information from the continuum mechanics literature because it's a convenient, these are convenient stress and strain measures to work with in large deformation finite element analysis. So this is the stress and that is the strain we will be using. And let me say the following now. This T here, the upper T, means stress at time t. In the configuration at time t, this lower 0 means that the stress is referred to the configuration at time 0. Similarly for the Green-Lagrange strain. Upper left, the configuration in which the strain or stress measure is measured, and the lower subscript means to which the configuration is to which the measure is referred to. So this is something to keep in mind because we will be encountering this quite a bit. Here is the definition of the stress tensor. T0 Sij, once again, the stress in configuration T referred to the configuration at time 0. Ij, of course, being the Cartesian coordinate components. Here we have the mass density ratio, the mass density at time 0, in configuration 0, if you like, the mass density at time t, in configuration at time t. And here we have a new quantity, which is actually the inverse of the deformation gradient. This is a component of the inverse of the deformation gradient. We will talk about this quantity quite a bit just now. Here we have the Cauchy stress. And here we have another component such as that one. This is the second Piola-Kirchhoff stress. Once again, I will talk about this piece of information quite a bit just now. The Green-Lagrange strain tensor is defined as shown here. T0 epsilon ij, ij of course being the components into the Cartesian coordinate axis, 1/2 T0 ui, j plus T0 uj, I plus T0 uk, I times T0 ukj. Notice that here we would select a particular I and j, say I equals 1, j equals 2. We would substitute those I and j numbers in here, so to say, and here as well, and notice that this k then would actually run over all possibilities, k going from 1, then to 2, then to 3. In other words, there's a summation involved here. By the way, similarly, we have a summation involved here because m and n would run over all the possibilities. I will talk just now a little bit more about it, but let's first now look at how this particular piece of information here is defined. It's defined as the partial of 0xi with respect to txm. Notice that this coordinate, of course, is given, is assumed to be given, and that one here is also now assumed to be given. Notice, of course, that txm is equal to 0xm plus the displacement that has occurred. Notice that this differentiation here is defined as given here. Partial tui with respect to the original coordinates. So this lower 0 here, refers to the fact that we're differentiating with respect to the original coordinates. This upper t here means that we are differentiating the displacement at time t. Notice, of course, that I and j are dummy indices here, so in fact this one here is what I'm considering, but at the same time I'm considering that one if I just switch around I and j. So these are the definitions of these two quantities, and I mentioned briefly already that we are summing in these definitions. For example, TS11 would be calculated from the formula that I gave you as 0 rho over t rho. This, of course, is a scalar, times this product here. What do we do here? We are selecting the 1 as that one here. That one here refers to that one. And then we are letting these components here these components here and that one here run over all the possibilities. Notice here we have 1, 2, that is this one here, and that one 2. And here we have 3, 3, 3, and 3. So in other words, these first two are fixed. These first two here are fixed, this one and that one. They correspond to this one, to these two ones, but the other components vary over all the possibilities, namely 1 to 2 to 3. This is here the summation convention, which is abundantly used in continuum mechanics, and you might be very well familiar with it. Using the second Piola-Kirchhoff stress and Green-Lagrange strain tensors, and that is really the important point now, we can rewrite the basic equation of the principle of virtual work in the form given here. Here on the left-hand side, we have the Cauchy stresses times the variations on the infinitesimal strains, or the small, infinitesimally virtual small strains. We integrate this product over the current volume. And we mentioned already that we cannot deal with this integration very well. Well, we can rewrite this integral as shown here. Second Piola-Kirchhoff stresses times variations in the Green-Lagrange strains. And we are integrating this product over the original volume of the body. And that is the clue. We know this volume, whereas in general incremental analysis, we would not know this volume if, for example, we only have calculated the response up to t minus delta t. So if we know this volume, we can directly deal with this integration. And we will see also that since these stress components are always referred to the same volume, the same area, we can also incrementally decompose these stresses, and the same holds for the strains. Notice this relation, of course, holds for all times, delta t, 2 delta t, t plus delta t. The way we talked about the principle of virtual work just now, we really had on the left-hand side here t plus delta t. Well, you would just exchange this t, that t, and that t, and that t here to a t plus delta t. And similarly, of course, on the right-hand side as well. I chose at the preparation of the view graph to simply call it t, because after all, this equation holds anyways for any of those particular times. To develop then the incremental finite element equations, we use the principle of virtual work in this form. If we assume that the response has been calculated from time 0 to time t, we apply the principle of virtual work at time t plus delta t. We integrate now over a known volume, as I pointed out, and we can directly decompose the stresses at time t plus delta t and the Green-Lagrange strains at time t plus delta t as shown in these equations. Now notice that here we have the stress at time t plus delta t referred to the configuration at time 0 being equal to the stress at time t referred to the configuration at time 0 plus an increment that is also referred to time 0. And this is what we would like to see. Similarly for the Green-Lagrange strain. These two items make it for us possible to work very well with the principle of virtual work in this particular form. Before developing, however, the incremental continuum mechanics equations, I'd like to discuss with you now some important kinematic relationships that we use in general nonlinear analysis. The second Piola-Kirchhoff stress and Green-Lagrange strains are have some very interesting properties that I think I'd like to share with you in a discussion. To explain some of these properties, we want to introduce the deformation gradient tensor. The deformation gradient tensor is actually something very, very basic in continuum mechanics. And so let us spend a little bit of time on this tensor to get also a bit of a physical feel for what it means, what it stands for, and what can we do with it. The tensor captures the straining of the body and the rotation of the body. And as I mentioned, it is really a very fundamental quantity used in continuum mechanics. The definition of the deformation gradient is as follows. Here we have T0x being equal to a matrix, a large matrix, which of course is written in a Cartesian coordinate system. And notice what we are doing in the elements of that matrix. We take the partial of Tx1 with respect to 0x1. In other words, we are taking the coordinates at time t and differentiate them with respect to the original coordinates. Here, the one component with respect to the one component. Here, the Tx1 with respect to the 0x2. And Tx1 with respect to 0x3. Like that, we get a 3 by 3 matrix. Using indicial notation, we can simply say that an element of that matrix, T0xij, capital X, because the matrix is defined as a capital T0x, being equal partial of Txi with respect to 0xj. Of course, ij are those ij's here. And you will also find in the textbook the following notation here, T0xij. Notice when I have a comma here, we denote the differentiation by that comma, and we use a little x. That is different from using a capital X here with no comma, because that capital X simply denotes a component of, let's go up here once more, the T0x of that matrix. So this is a mathematical definition, really, of the deformation gradient. And notice that in order to calculate the elements of this matrix, of course, what you need to be given is this Tx1, Tx2, Tx3 as a function of 0x1, 0x2, and 0x3. If you are given the deformation field Txi as a function of the 0xj's, then you can calculate directly the components of this 3 by 3 matrix. Another way to write the deformation gradient is via this equation. T0x can be written as 0 del 0. This is here the gradient operator. Let's look down here. We have defined it here. Times Tx, or this gradient operator operates, I should say, on Tx capital T. This capital T means transposed. And this Tx capital T is given right here. Notice what we are listing in this vector here now, in this row vector, are simply the coordinates at time t, Tx1, Tx2, Tx3. Notice that there is a transpose here. That transpose is simply introduced to make sure that this right-hand side is equal to what we have defined on the previous view graph, this to be. If you leave out that capital T, you would not quite get what we actually have defined on the previous view graph. So that's why we put that capital T in there. It would be a nice exercise for you to just actually substitute from here into there, plug into there, and write out the 3 by 3 matrix to make sure that you actually get what's given here on the left-hand side, the way we defined it on the previous view graph. The deformation gradient, as I briefly mentioned, describes the deformations, the rotations and stretches of the material fibers. Let's look at some examples now. For example, if we have D0x here, that is a material fiber in its original configuration. Of course, that original configuration is going to be deformed, moves through the stationary coordinate system. That fiber moves into this situation here. It becomes dtx. The deformation gradient gives us this element as a function of that element as given in this equation. In other words, dtx is equal to T0x times d0x. if you know this piece of information and you have calculated the deformation gradient, you directly get dtx. That's what the deformation gradient does for us. Well, an example. It's always nice to look at some examples to demonstrate what we mean by these theoretical formulas. And here we have a very simple example. It's a one-dimensional deformation. We start off with this piece of material, a rectangular piece of material, and that piece of material is stretched out from time 0 to time t into this red configuration. Quite a bit of stretching, but the motion is simple because it's a uni-actual motion. Notice the original length of this piece of material is 1, and this side here moves out 0.5. Of course, the material particles here will move. For example, a particle that was originally here, the black little line there, will move over to the right, and it becomes this red little line. This black line moves over to become that red line. Notice the displacement of this black line is given by this blue arrow here. This black line moves over to there, and the displacement is given by that blue arrow. If we know the displacements of all these particles here, we know the deformation field. Vice versa, if the deformation field is given, and now we look at this equation here, we know the displacements of all the particles along. And Tx1 is equal to 0x1 for this particular deformation field plus 0.5 0x1 squared. Let's look at what this means. It tells that if I plug in a particular coordinate on the right-hand side of a material particle in its original configuration, then I'm going to get the final coordinate of that same material particle. Well, the deformation gradient is defined via this relationship, and it's therefore given as 1 plus 0x1. Notice we have only motion in one direction, so we only calculate this one component. Let's consider, quite physically, a material particle initially at x1 equals 0.8. In other words, x1 is this direction. 0x1 is equal to 0.8. Remember, x1 just gives us the coordinate direction. We now put a 0 on it to signify that 0.8 is the position of the particle initially. That particle moves with the deformation field that I've been given to this point here, and Tx1 is then 1.120. The same can, of course, be repeated for an adjacent material particle. In other words, let us look now at a material particle that is just a little bit to the right-hand side, namely 0x1 being 0.850, slightly to the right-hand side of the other material particle that we looked at. This material particle, with the deformation field that we have been prescribing, moves to Tx1, this number here. We can now compute T0x11, the element of the deformation gradient, as this difference here, and the numbers are plugged in here, and we obtain 1.82. Of course, this is an estimate because we did not take a differential. If we actually calculate the deformation gradient the way it's being defined, we get 1.80, which is quite close to the estimate here. The reason for that difference, of course, is that 0x1 for this particle is not close enough to the earlier particle, the other particle that we also looked at. In other words, 0.850 is not close enough to 0.8 in order to get a very close relationship here between these two numbers. Let's look at another example, a two-dimensional deformation example. Here now we have, as the original configuration, this black body here, black outline shown, in the coordinate system x1, x2. Once again, remember the coordinate system is stationary. And let us look at two material fibers, this one and that one. This one does not carry a hat, that one carries a hat. So these are two different material fibers. These fibers move to here, from time 0 to time t. This fiber d0x becomes dtx, that fiber d0x hat becomes dtx hat. In other words, of course, this here in red shown is the configuration at time t. Now, notice that these fibers here have particular coordinates, 0x1, 0x2. You can think of these coordinates to be at the beginning of that fiber. Of course, these are differential fibers. They are very, very small. These coordinates move over to tx1, tx2. In other words, the particle from here moves to here and takes on these coordinates. We also say know that the whole, we also know the whole deformation field, and therefore we can directly calculate the deformation gradient, the way I explained it, by taking the differentiation of the current coordinates with respect to the original coordinates. And those differentiations give us these elements. If we do so, we have the relationships between the d0x and dtx given right down here. Notice d0x has these components in the x1, x2 coordinate frame, and you can see, for example, this 0.866 is the component in the x1 direction. This 0.5 is a component into the x2 direction. If we multiply this out, we get dtx. And dtx, shown here, has no component into the x2 direction, but has a component of 0.75 long into the x1 direction. What this tells us is that if we know the motion of a body from time 0 to time t, and particularly at time t, and if we have calculated the deformation gradient, the way we have defined it, then we can relate how the original fibers, or the fibers in the original configuration, will rotate and stretch. And that relationship is given via the deformation gradient, as surely shown here quite physically, because this fiber originally here has rotated into a new position and has, in this particular case, been compressed. So this relationship tells us how the fiber has moved, rotated, and compressed. It does not tell us how much the movement was. That is not given by this relationship. That we have already, because we have to have that information to calculate T0x. But what this information, this equation gives us is how much the fiber has rotated and compressed or stretched. Well, let's look at another fiber, the one that we had on the earlier view graph. Here, another fiber. And if we recognize, of course, that for that material particle here, the same material particle still, we still have the same deformation gradient, we can take this fiber, or rather the vectorial representation of that fiber as given here, multiply this out, and we directly find out what has happened to that infinitesimal fiber in the motion that we are considering. Notice in this particular case, the components of this fiber are 0 in this direction, 1.5 into that direction, and it has moved to here and has taken on components 1 and 1 into each of the coordinate directions. The deformation gradient is very useful for various measures, computations that we perform in finite element analysis. And one such computation is to calculate the mass density ratios. In other words, we have to assess how the mass density of the body, as it moves through the space, changes. Let us look at how we do that. Here we have our stationary coordinate system x1, x2, x3. And in that stationary coordinate system, I like to focus our attention onto a differential volume, a very small volume. I call that 0dV curl, a curl there, because it is a specific volume that we now want to look at. Notice that the volume that I'm talking about here is spanned out by the differentials d0x curl 1, 2, and 3 not shown. But this is the infinitesimal volume at time 0. Now, in the motion from time 0 to time t, of course, this volume will change. And at time t, it looks like this. Notice that these differentials here have changed. We show just one, d0x curl 1 has gone over into dtx curl 1. The t now denoting time t. And this is a volume obtained from, well, that can be calculated from these vectors shown here. And in fact, this is how we calculate this volume and can therefore relate also the mass densities. Let us look at some of the basic equations. First of all, we can say that the mass in this volume, this differential volume that we have focused our attention on, and that I have given a curl for that reason, that mass must be preserved. And this means that this relationship must hold. Volume times mass density at time t must be equal to volume times mass density at time 0. We can show then that this relationship holds, and I will talk about that just now a little bit more. And these two relationships then clearly give us that this is how the mass density changes. In other words, the mass density at time t can directly be calculated from the mass density at time 0 and the determinant of the deformation gradient tensor. Notice in three-dimensional analysis, this is a 3×3 matrix, and you would have to calculate this matrix at the particular point that you're focusing your attention on and take the determinant of that matrix. Let us look at this relationship here, because that is a very basic relationship. It tells how the volume, the differential volumes change as a function of time. And to show you how we arrive at this relationship, I've just compiled here a few view graphs to give you the proof. Initially, we can say that d0x curl 1 is given via this relationship. Notice this is the length of this vector, simply. And notice that I had aligned this vector with the x1 coordinate axis, therefore these zeros. Similarly, d0x curl 2 was aligned with the x2 coordinate axis, and therefore these two zeros. And the length of the vector is ds2. dx curl 3 is given similarly, but aligned, this vector is aligned in the 3 direction, and the length is given as ds3. Hence, by simple calculation, of course, we find directly that the volume, the differential volume, that in the original configuration is given via this equation. But if we now recognize that we can express dtx curl I via this relationship here, and that is nothing else than applying the deformation gradient tensor the way we already talked about it. We looked already at examples where we put in a particular fiber, original configuration, and calculated how this fiber stretch deformed from time 0 to time t. I just gave you some examples. And we use that information now here to express the dtx curl I in terms of d0x curl I. Of course, for I equals 1 to 3. And now we use here a formula that you must have encountered some time ago in your studies of mathematics. If you look at your old math books, I'm sure you can extract that formula, which simply says that the volume given spanned by these vectors is given via this product here, the cross product of these two vectors and the dot product of the resulting two vectors. This, of course, gives you a vector here, and you dot this vector with this vector, and you get directly a number, which is the volume of interest. However, if we now multiply this out here, you find directly that this is the answer. In other words, the deformation gradient comes in right there. The determinant of the deformation gradient comes in here. Of course, it comes in here because you would substitute from here into there. And once again, since this product here is nothing else than the original volume, we are home. We have proven that dt v curl is equal to the determinant of t 0x times 0 dv curl, the determinant of the deformation gradient in this relationship between the differential volumes. It's really an interesting proof, and maybe you want to think a little bit more about it and even go through this arithmetic here to really reinforce the understanding of what we are doing here. Let's look at a simple example to just exemplify once again what we just talked about. Here we have a little example, a piece of material 1 long, that in its original configuration is 1 long, I should say. We are stretching that piece of material up to time t as shown. We assume uniform stretching. We assume plane strain conditions. In other words, the strain through the thickness is equal to 0 here in this particular case. And the deformation field is assumed to be as shown here. Then, with the deformation field given, clearly we can calculate this deformation gradient. Here, this component is simply obtained by differentiating tx1 with respect to 0x1. If you do so, you get a 1 here plus 0.25, giving you a 1.25. Because there is no shearing in the material and no rotation, these off-diagonal terms are 0. And because there is no stretching through this direction and through the thickness direction, we have 1s right there. To take the determinant of this matrix is rather simple. You just take the product of the diagonal terms, and you directly obtain 1.25 for this determinant. Now, let us plug this into our formula. And here we have the result of that formula. It tells us 0 rho is equal to 1.25 t rho for any particle right here, because this relationship is independent of the 0x1 component. Well, of course, this is also a result of the uniform stretching. Notice that this makes physical sense if we have taken a piece of material up here. Once more, let's look at it. That does not shrink here, that does not stretch or shrink in this normal direction as well, then surely the mass density has to decrease as we stretch it. And in fact, this is being shown right down here. T rho is equal to 0 rho divided by 1.25. So the result makes sense. We use also the inverse deformation gradient. And here on this view graph, I've just summarized a few equations regarding this inverse deformation gradient. Here we now look at an equation where on the left-hand side we have the material fiber at time 0, and on the right-hand side the material fiber at time t. In other words, d0x on the left-hand side and dtx on the right-hand side. The inverse deformation gradient stands right here. Mathematically, we can show that the inverse deformation gradient is nothing else than t0x inverse. Of course, notice that 0tx would be calculated by differentiating the original coordinates with respect to the coordinates at time t. However, we can also calculate this matrix directly by taking this matrix here, where we differentiate the coordinates at time t with respect to the original coordinates, and then, having obtained this matrix, calculate this matrix, we simply invert it. Well, the proof that this indeed holds is given down here in green. We simply take the top equation and substitute for dtx as shown here, our relationship that we had already earlier. And if we then look at this equation, we can put brackets around here. And since d0x is equal to d0x for any material fiber, this must be the identity matrix, which already completes the proof. An important theorem in continuum mechanics is the polar decomposition theorem, which tells that the deformation gradient T0x can always be decomposed into a rotation matrix and a stretch matrix. The rotation matrix is an orthogonal matrix, of course, meaning that R transpose R is the identity matrix, and the stretch matrix is a symmetric matrix. This can always be done for any x, and the proof actually is given in the textbook. Please look at your study guide where I indicate where you can find the proof in the textbook. And it might be quite good to actually go through that proof in some detail so as to reinforce your understanding of what this theorem really tells. The important point, once again, is that we can always write the X matrix into this form as R times U. And to give you an example of what this means, let's look at this one here. Here we have in the coordinate frame x1, x2, a piece of material, 3 long, 2 wide. This is the original configuration of the material. And that material moves from time 0 to time t as shown here. First it moves, it is being stretched into the x1 direction and into the x2 direction to take on the configuration shown in red. And then it rotates to take on the configuration in green, and that indeed is the configuration at time t. Let us calculate the X matrix corresponding to that configuration and see how it would be decomposed into R times U. Well, we have done that down here. Notice this is the X matrix, T0x. These are the components of that matrix. And here we have the R matrix, T0R, and here we have the T0U. In other words, this is the rotation matrix, and this is the stretch matrix. Notice this stretch matrix is indeed symmetric. Let's look at the components in the stretch matrix a little bit closer. 1.33 is nothing else than 4 divided by 3. In other words, the stretching into the x1 direction. 1.5 down here is nothing else than the stretching into the x2 direction. Namely, 2 goes over into 3. 3 divided by 2, 1.5. Notice that these off-diagonal elements are 0. The reason being that there has been no shearing from the original configuration to the red configuration. The rotation matrix really expresses mathematically the movement of this red piece of material into the green configuration. Notice that the entries in this rotation matrix are nothing else than cosines and sines of this 30-degree rotation. For example, here you have the cosine of 30 degrees. This is the sine of 30 degrees. In fact, it's the rotation of this material fiber right there, from here into there. Well, this is the rotation matrix and stretch matrix for this example, and we could easily construct other examples. In fact, you find in the textbook some more examples that you might want to study regarding this particular phenomenon. Using the deformation gradient, we can define a Cauchy-Green deformation tensor. It is the right Cauchy-Green deformation tensor. There is also a left Cauchy-Green deformation tensor, which, however, we will not be using. So when I talk about the Cauchy-Green deformation tensor, I really mean the right Cauchy-Green deformation tensor. And it's defined as shown here. We take the deformation gradient transposed times the deformation gradient. Now notice the deformation gradient is always a 3 by 3 matrix in a 3-dimensional coordinate space. However, it can be a non-symmetric or symmetric matrix. Generally, it is a non-symmetric matrix. It would be a symmetric matrix if there has been no rotation, for example. But in general, it's non-symmetric. Notice that this non-symmetric matrix multiplied here as shown by the non-symmetric matrix transposed makes C symmetric. A very important information. Well, indeed, if we substitute for x here, we find that C is nothing else than T0 U squared. In other words, the stretch matrix squared. Since R is orthogonal, R goes in here, but R transpose R, of course, is the identity matrix, and therefore C is simply U squared. Notice that T0C is independent of the rotation via this equation here, and therefore we say that C is invariant under a rigid body rotation. In other words, a rigid body rotation of a material fiber does not enter into the elements of C. Let's look at an example. Two-dimensional motion. The original configuration for the piece of material that I like to consider is shown here. It moves from time 0 to time t to the red configuration, and then in the increment of time delta t to that green configuration. But this movement over time delta t is simply a rigid body motion of 90 degrees. Well, we can calculate T0x corresponding to this configuration. Here it's done. And by the formula that I gave you, you get directly T0c by taking x transpose times x. You get this matrix here. Well, now we can also calculate T0x. How do we obtain, by the way, this matrix? There's a subtle point. You obtain this matrix simply by pre-multiplying this matrix by a rotation matrix corresponding to this 90-degree rotation. This is the answer. And if we now take this matrix transposed by the matrix itself, in other words, this product x transpose x, we get the C matrix, and we notice that the C matrices are the same for both of these configurations. In other words, this simply exemplifies that the rigid body rotation from red to green here did not enter into the elements of the C. They did not change from time t to time t plus delta t. We use this C matrix to define a strain measure, the Green-Lagrange strain measure. It's, of course, a strain measure that is very well known, described in many, many textbooks. And it is, however, very useful for finite element analysis, as I briefly pointed out already earlier. This is the definition of the Green-Lagrange strain tensor. Notice this here is a 3 by 3 matrix. And we are taking this 3 by 3 matrix, we subtract the identity matrix. The identity matrix, of course, being just ones on the diagonal and zeros on in all the off-diagonal elements. And there's a 1/2 here. That gives us the definition of the Green-Lagrange strain tensor. There are a number of very interesting properties that this strain tensor displays, and I've listed them here. We can see that this strain tensor is symmetric. We can see that this strain tensor does not change from time t to time t plus delta t if the only motion from time t to time t plus delta t was a rigid body motion. And we can see directly that the Green-Lagrange strain tensor is 0 if from time 0 to time t the only motion was a rigid body motion. One can prove these particular items, these statements, and I would like to encourage you to do so. While you are doing it, I will do the same here, and then we share our experiences regarding these proofs just afterwards. Well, here I am giving now to you some information regarding these proofs. T0 epsilon is symmetric because T0c is symmetric. And remember, we're taking here a symmetric matrix from which we subtract a symmetric matrix, and clearly the result must be a symmetric matrix. A very simple proof, really. Regarding the second item that I mentioned earlier, for rigid body motion, we know that from time t to time t plus delta t, we have that x from at time t plus delta t can be written as r times t0x. In other words, here I am talking about the deformation gradient at time t plus delta t, and here about the deformation gradient at time t, and they are related merely by a rotation matrix. Now, if you substitute from here into this equation, but apply the time t plus delta t, you obtain, of course, as we saw actually on the earlier example, that this C matrix does not change, and therefore also the Green-Lagrange strain tensor does not change. In fact, all of this information was really addressed in the earlier examples that we discussed. Also, for rigid body motion, we have that the C matrix is simply the identity matrix, because remember, the C matrix, Cauchy-Green deformation tensor, does not change with rigid body rotation. It is equal to the identity matrix, and if you then take this C matrix and substitute right up there on the top, you get that the Green-Lagrange strain tensor is 0. So three properties really that we want to keep in mind regarding the Green-Lagrange strain tensor when we later on use it. Another definition of the Green-Lagrange strain tensor is given on this view graph. In fact, this right-hand side that I'm showing here is simply obtained by substituting for the deformation gradient the identity matrix plus the deformation, while the displacement derivatives with respect to the coordinates. In other words, what you want to do basically is to substitute for t0x in terms of displacements. And if you go through and write all the information out, you end up that the t0 epsilon ij component of the Green-Lagrange strain tensor is given by this equation here. Notice that we have here ij, the same subscript that you see here too. Of course, we are differentiating with respect to the j component here. Here we have ji, and here ki, kj. We are summing over k here. Notice also that this part here is nonlinear in the displacements. This part is nonlinear in displacements because these are, so to say, quadratic terms. This part is linear in displacements. From time to time, students approach me and say to me, well, you must have neglected something in the definition or in this Green-Lagrange strain tensor. Because you're only going up to quadratic terms, you must have neglected cubic terms and higher order terms. Well, the answer there is we have really neglected nothing. The point is that we have defined this tensor to be given by this equation. Of course, my earlier definition was in terms of deformation gradients, in terms of the deformation gradient. Now we actually have here substituted displacements. But it's still a definition. This is in fact the same tensor, the same components here would be calculated using the earlier definition than this one here. Same thing. And as I say, it holds for any deformation, any amount of straining and stretching. Let's look at one example, a very simple example, where we have a simple 4-node element that we are pulling out. Originally, it is in the black configuration. It goes over into the red configuration. If we calculate T0 epsilon 1, 1 from the formula that I just showed you, you get these two terms. This here is the engineering strain term that we are very well familiar with. And this is here the nonlinear term, because it's a quadratic term, nonlinear in the displacements, of course. If we plot this information as shown here on the graph, notice we are showing here T delta over L, the original length, where T delta is the displacement. And we are plotting here the epsilon 1, 1 component. Actually, we should have said here, and let me make this correction right now here, we should have really have had here a T0 epsilon 1, 1. The T0 was missing there. Well, if we plot, in other words, this component here as a function of these elements here, of the T delta over 0L, we get this red line, the red line. Notice the nonlinearity in that strain. The engineering strain, which is only the first term here, gives us the straight line. Notice that this strain here increases quite rapidly as you pull out, and it decreases in magnitude here with this curvature as you push in. So there is no symmetry in the strain when you extend or compress a piece of material. In the engineering strain component, of course, we see a symmetry because we have a straight line. Let us look at another example to calculate once the Green-Lagrange strain. Here we have the original configuration of a 4-node element, and that 4-node element, shown black here, goes over into this configuration at time t, stretched into two directions, and then at time t plus delta t, it has rotated by 45 degrees. The deformation gradient corresponding to time t is shown here. The Cauchy-Green deformation tensor shown here. Notice no off-diagonal elements because the piece of material, the 4-node element, you may think of this as a 4-node element, of course, has simply been stretched and compressed. There's no shearing. Therefore, we have 0 terms here. And if we calculate the Green-Lagrange strain tensor, we get this answer. Once again, no shearing components in this tensor as well. If we now do the same for the configuration at time t plus delta t, the green configuration, we obtain this deformation gradient, this Cauchy-Green deformation tensor, and this is the Green-Lagrange strain tensor, where we notice that the Cauchy-Green deformation tensor has not changed, and the Green-Lagrange strain tensor has also not changed. And this is what, of course, we have proven already earlier, that from time t to time t plus delta t, the Green-Lagrange strain tensor and the Cauchy-Green deformation tensor, both of those do not change. However, for rigid body motion, the x tensor, deformation gradient, does change. Look at here, because this deformation gradient is affected by the rotation. Let's look at another example, because all these examples really enrich our understanding of what these kinematic quantities stand for and what they give us. Here we look at the example of a simple shear deformation. Originally, the element that we're looking at is in this configuration, and it is sheared over. You can think of this top line being simply moved over horizontally into the red configuration. Notice that the original length here is 1. This length is also 1. Notice that the movement over is t delta. And we calculate the deformation gradient once again. The deformation gradient now being given via these components. Let's try to explain these components a bit. Well, this here is really the differentiation of tx1 with respect to 0x1. Now tx1 has not changed, and therefore this is 1. tx1 is equal to 0x1 in other words, and therefore this is 1. Notice that the same holds also for partial tx2 with respect to 0x2. Notice that this element here stands for partial tx1 with respect to 0x2, and there we look at partial tx1, a change into this direction as we walk that direction, and that gives us this t delta over this length here. In other words, this element is nothing else than this length divided by that length, and it's of course the same for any material particle over this domain, because all of these material particles have been shared over. Well, if you now take x transpose times x, you get this matrix here, and you identify directly these terms. If we then calculate by the formula given the Green-Lagrange strain, this is the result. Notice that here we have now shearing components, and notice also one very interesting phenomena, a component appearing here. This is an interesting component because it is really a normal strain component in this direction. In other words, an epsilon 1, epsilon 2, I should have said, component, an epsilon 2 component that is non-zero in this particular case. In a materially nonlinear only formulation, where we only include infinitesimal displacements, in other words, this part, of course, would be 0. And that is also signified by the square term. In other words, if indeed the motion is small in this direction, then this would become 0, at least approximately 0, when compared to these terms. And it means that the Green-Lagrange strain tensor reduces to the infinitesimal strain tensor that we are so familiar with. The second Piola-Kirchhoff stress tensor and the Green-Lagrange strain tensors are energetically conjugate. This is a very important statement, and this is the reason why we are working with these two tensors, the second Piola-Kirchhoff stress tensor and the Green-Lagrange strain tensor. In fact, what is happening here is that this product here, which is the virtual work at time t per current volume, per unit current volume, that this here is given, of course, by the Cauchy stress times the small or the virtual infinitesimal strain, is defined this way. And here we have the virtual work at time t per unit original volume. And that is given by the second Piola-Kirchhoff stress times the variation in the Green-Lagrange strain. We already had earlier that the integration of this over the current volume is equal to the integration of this quantity over the original volume. Well, this is here once more something to be kept in mind, but the important point is that the energy that these two quantities are energetically conjugate, and this is expressed via this product here. Let's look at the second Piola-Kirchhoff stress tensor now. The second Piola-Kirchhoff stress tensor in indicial notation is defined as shown here, and we had already that definition earlier on a view graph. In matrix notation, we can directly say this is the way you can also write it. Notice that the entries in this 3 by 3 matrix, I'm always thinking about 3 components, or rather a 3-dimensional coordinate space. The entries here are nothing else than those elements. The entries of this matrix, of course, are those elements here. And similarly here, this is the scalar that we talked about earlier already. If we solve from here for Cauchy stresses, we directly obtain these two equations. Notice that in this matrix notation now we have the deformation gradient, whereas in the earlier equation that we looked at here, we had the inverse deformation gradient. Well, these are relations that we want to keep in mind and that we will be referring to quite abundantly later on. Let us look at some properties of the second Piola-Kirchhoff stress tensor. First of all, T0s is symmetric. Well, that can be seen directly by looking at the definition. You might want to prove it to yourself with a small example as well. T0s is invariant under rigid body motion, translation or rotation. Hence, T0s only changes when the material is actually deformed. This is a very important statement and important fact, I should say, and we want to look at an example just now. T0s has no direct physical interpretation. Well, if you look at some books, you see some pictures regarding T0s, regarding the second Piola-Kirchhoff stress tensor. In fact, I have some pictures in my book, in an example there. But these pictures are quite far-fetched, and they really don't give as deep a physical insight as one would like to have with a stress measure. I personally like to now take almost the attitude of saying, well, I accept that there is no real strong physical interpretation of this stress measure. It is used because it's a convenient stress measure to deal with. We would not, in an engineering analysis, really print it out in a computer program. As I said earlier, we would, of course, want to have the Cauchy stress as the stress measure with which we want to design our structure. I look at it as a measure that is convenient to work with in the engineering analysis. It's interesting, of course, from a theoretical point of view to look at the elements and to see how large they are. how small they are when compared to the Cauchy stress, the real physical stress that we're interested in. But we don't really need to look for a strong physical interpretation. I know we are engineers. Engineers like to see pictures, like to understand physically what's happening, and I can assure you that I've tried myself quite hard to get a physical interpretation of this, this definition of this second Piola-Kirchhoff stress tensor, but I have not arrived with many good results. The best I could do is given in my textbook, in the book that you are using as a textbook. Let's look at an example here. The example of a 4-node element being stretched and rotated as shown here, and then rotated as shown here. Notice that from time t, shown as the red configuration, to time t plus delta t, we have only a rigid body motion, a rotation of 60 degrees. Of course, the material would be subjected to some Cauchy stresses, and Cauchy stresses in this configuration and Cauchy stresses in this configuration. Let us see how the Cauchy stresses and how the second Piola-Kirchhoff stresses evolve during this motion. And on this view graph here, we have summarized that information. At time t, the deformation gradient is as shown here. The Cauchy stresses, say, are like this. Of course, we would have to introduce a material law, etc., etc. Let's just assume that the Cauchy stresses are like that. And then, given the Cauchy stresses, the deformation gradient, we calculate the second Piola-Kirchhoff stress tensor. Let's say that this has now been calculated, and we do the same at time t plus delta t. We know that there has, of course, been additional motion from time t to time t plus delta t, which means that these elements here will change, and you should now be in a position to calculate this tensor, because you know there's only a rigid body motion that is being applied. And then, knowing this tensor, we can directly also calculate the second Piola-Kirchhoff stress tensor, and we can calculate the Cauchy stress tensor. So we can really calculate all of these, and what do we see? This is the really important point. We see that the second Piola-Kirchhoff stress tensor has not changed from time t to time t plus delta t. This is the important information that I mentioned earlier. However, the Cauchy stress tensor, of course, has changed. The Cauchy stress tensor has changed. One can, of course, prove that the second Piola-Kirchhoff stress tensor does not change when the material is only subjected to a rigid body motion, and such proof is actually given in the textbook. But this is a simple application, and it exemplifies to you what I mean by that statement. It's an important statement that you should keep in mind as we go along with our further discussion of the mathematical basis of nonlinear finite element methods. This brings us then to the end of this lecture. I have tried to give you some of the mathematical basis, some of the ingredients rather, that we are using in finite element analysis. We have discussed stress and strain measures that we will be encountering further in the next lectures. Thank you very much for your attention.